This is Lab 1 for Physics 1, dealing with one-dimensional motion. The purpose of this lab is to observe an object moving in one-dimensional motion at a constant velocity. The principles behind this lab deal with the velocity update and the position update formulas. Due to our assumption of constant velocity, however, net force is 0, making our velocity update obsolete. Therefore, V average equals V initial. Our goal is to get a chart looking somewhat like what we have in the bottom right, where we plot position against time due to it only being in one dimension, measuring simply how far away it is from the origin, where for every time step the object moves the same amount of distance. The observation of this lab was an expo marker, the system, rolling across a table, which, including the Earth, is the surroundings. The yardstick is simply for reference for the tracker video. The expo marker rolls across the purple x-axis overlaid onto the video. That is our one-dimensional motion. And using the tracker software, I can track how far it travels, given by this chart up in the top right. Now, this data will be different from the data displayed later on because the screenshot is from after it accidentally deleted the data I used to make the chart later on. After the observation, I set up a computational model based on the observation. Using the data from the tracker, I was able to input a position and velocity vector that the tracker gave me. Our t is until 0.8 because that is what the original tracker video was, until 0 to 0.8 seconds. Our force is 0 because, once again, we're dealing with constant velocity. And then we input the velocity and position updates. Our velocity update is once again obsolete, and only our position update is really necessary. And that is going to be shown in this video by an object moving along the x-axis, as well as a graph of position against time being drawn. And as we can see, like before, we have our linear graph of position against time that is desired. Moving on, now I can take the data from the observation and the computational model and plot them against each other, with the darker color being the computational model and the lighter color being the video. Now what we can see is that at the start they were almost exactly the same due to, well, the observation's initial velocity being used to input the velocity of the computational model. So those will be pretty much the exact same line. However, as we progress through time, the video tracker, that line veers off, and that is due to frictional forces acting upon the marker, slowing it down as it travels, something that the computational model does not deal with. Some other errors is that the video tracker could be slightly off, as my camera was slightly shifting due to just like my arms being unsteady, as well as just the slipping and compression forces that apply friction and the loss of energy to the marker as it rolls. What if we were to flip the axes, say it's traveling along the negative x direction rather than the positive x direction, then if we take that chart from last slide, where we plot the data together, extend it down below the x-axis, then simply we would draw the tracker traveling down into the negatives, just reflect it over the x-axis. What does it mean? Well, in the observation, we have gravity pulling the marker down. We have the table applying a normal force up to keep the marker from phasing through the table, and those cancel out to give 0. However, unfortunately, friction exists, and even for a rolling object, it will still slow it down. Due to the fact that I was not continuously pushing the marker with my finger while I was recording, and instead I applied an initial force and then recorded, that will slow it down. There is no force to counteract the frictional force, and therefore the marker will slow down. So there is not zero net force in the observation. However, in the ideal, I would have been continuously pushing the marker through to counteract any friction.